learning today we can do now. So let's consider a figure skater. Okay, so if you have a figure skater rotating at a constant velocity, okay, and her arms are spread wide, then she contracts her arms towards the center of her body, so towards her center of mass. Describe what you will observe. So take a minute and pause the video. You're going to jot this down in your notes. When you're ready to discuss, you're going to unpause the video. Okay, so if our ice skater is initially rotating at a constant velocity, and she contracts her arms towards the center of her body, the force is internal to the system, right? There is no external force applied to the system. So if there is a lack of an external force, we know that momentum must be conserved. Okay, in this case, the angular momentum must be conserved. So if angular momentum must be conserved, she will reach some final constant angular velocity. Okay, if her arms contract, right, the radius of rotation is going to decrease. If the radius of rotation decreases, the angular velocity must increase in order for the product of the moment of inertia and omega to be constant. So she will reach some constant angular velocity that's greater than her initial angular velocity because the radius of rotation decreases. So to help kind of visualize this, we're going to take a look at a simulation. Okay, so the first simulation we're going to look at is just a box. Okay, and that box represents the center of mass of the object, or the location of mass of the object. Okay, so our box is rotating at a radius r at some constant angular velocity, 50 revolutions per minute. An internal force to the system is applied, meaning that the radius of rotation decreases. When the radius of rotation decreases, we see that the system meets new constant angular velocity that has a larger magnitude than the initial value. Okay, so for the case of this simulation, we're going from 50 revolutions per minute to 200 revolutions per minute. Okay, what about those ice skaters in which use one leg to rotate? So they have two arms spread, one leg to rotate. So as the skater takes her leg and then her arms closer to her center of mass, her radius of rotation decreases once when her leg moves in, and then twice when her arms move in. Okay, so when her leg is spread, just like when her arms are spread, her mass is concentrated further away from the axis of rotation. If the mass of an object is further away from the axis of rotation, the moment of inertia is larger. If I is larger, omega has to be smaller if angular momentum is conserved, which in this case we know it is. So why here, looking at the simulation, why here do we think that the magnitude of the angular velocity is increasing, but in the negative direction? Okay, so we know that the direction, when we're talking about angular velocity, corresponds to the direction of rotation. Right, so we see here that the ice skater starts with an angular velocity of negative 60 revolutions per minute. Negative means that she is rotating clockwise. Right, positive would be counterclockwise. So as her radius of rotation decreases, the magnitude of her angular velocity is increasing, but in the clockwise direction. Okay, so on the AP exam and on your unit test, you will see conceptual questions similar to this. So you'll be asked to quantitatively determine how angular velocity or radius must change if momentum is conserved. Let's look at some quantitative examples, again using parallel axis theorem and objects with multiple values of I.